Have you ever been in like a really crowded place, maybe like leaving a concert or trying to catch a train, and suddenly it's like everyone just comes to a standstill?
Uh-huh.
You're stuck shuffling along, and you can't help but think, what is it that causes this? Like, what makes a crowd go from moving smoothly to total gridlock?
Yeah.
We've all been there, right?
Yeah.
Well, today we are going to do a deep dive into the science of how crowds of people move.
Absolutely. And, you've brought some great material, a study in PNAS, and also reporting from Science Daily and Live Science.
Yeah.
And they all kind of point to some really interesting mathematical insights into how crowds move or, how they don't move.
Exactly. And what we want you, the listener, to get out of this deep dive is an understanding of the principle behind whether crowds move in an orderly way or if they just devolve into that kind of frustrating hooky-jerky mess. We want to give you a shortcut to understanding this fascinating area of research.
Yeah.
So, where do we start with this?
Well, the big thing here is something called the angular spread parameter.
Okay.
That's kind of the key discovery here that mathematicians and specifically Carol Bessick and his team at MIT have found.
Okay. Angular spread parameter.
Yeah.
Now, that sounds a little bit technical.
Yeah.
Can you explain in sort of layman's terms what this measures when we were talking about people in a crowd walking?
Sure. So basically, it measures how much variety there is in the directions that everyone in the crowd is walking.
Okay.
So, like, are they all generally moving in the same direction, or they try to go all over the place at lots of different angles?
So it's kind of how much everyone is trying to go their own way.
Yeah.
And is there like a tipping point with this parameter?
Yes. And this is where it gets interesting. The research points to a very specific range. It's between 13 and 16 degrees.
Okay.
So if the average difference in the directions that people are walking is less than this number,
Hmm.
then something amazing happens. People naturally form lanes almost like cars on a highway.
Wow.
And this happens totally spontaneously. There's no one telling them to do it. They just kind of do it.
So you're not even thinking about it when you're in a crowd. It just sort of happens.
Yeah. Right. And on the other hand, if that angular spread is greater than 16 degrees, then people don't form lanes. And that's when you start to see that chaotic stop and go movement that we're all familiar with.
So how did the researchers figure out this specific range of degrees? Like, was this just a theory or did they do some experiments?
Well, they took a really comprehensive approach. They used a few different methods. First, they used math to create models of how pedestrians move,
Okay.
and then they did something called agent-based computer simulations. So imagine they created little virtual people in a computer program and gave each of them simple rules about how to move and react to other virtual people.
Hmm.
Then they let all these virtual people interact in a virtual space. This allowed them to test out their mathematical models in a controlled environment.
Yeah, they also did real-world experiments too, right?
Yeah.
Didn't they use like a gymnasium setting?
Yes, they did.
Yeah.
They had over 150 participants over two separate sessions in a big gymnasium. And they very carefully designed these experiments to be able to control and change the angular spread of the pedestrians' movements.
Okay, so they were kind of subtly guiding people to walk at different angles relative to everyone else.
Exactly.
Yeah.
And to make sure they were tracking each person accurately, they came up with a really clever method. They gave everyone a regular hat, but they attached a unique barcode to the top of each hat. And then they set up cameras above the gymnasium to record every single movement that each person made.
Hats with barcodes.
That's such a cool image. I don't typically picture scientists doing research like that.
Yeah. It's pretty creative, right?
Yeah.
But it allowed them to very precisely track each person's walking path and how fast they were moving, all under very controlled conditions where they could adjust that angular spread.
No, it wasn't just theoretical. They had real-world data from people to back up their findings.
Okay.
So now we understand what the angular spread threshold is, and we can picture what it looks like when you have orderly pedestrian flow versus that chaotic, jumbled mess.
Right.
And we know how they cleverly used experiments to confirm all of this. But why does all this matter? What are the real-world implications? Well, the question is, how can we use this new knowledge in practical ways? And it turns out that this research has a lot of potential for improving urban planning and crowd management.
So it's not just some interesting academic finding. It could actually change the way we design and use public spaces.
That's right. So think about it from the perspective of urban designers and city planners. They are the ones who are responsible for creating safe and efficient pedestrian areas.
Okay.
And by understanding this angular spread parameter, they can start to optimize the design of things like sidewalks, crosswalks, even entire plazas to encourage people to move more smoothly.
Can you give like a concrete example of how this could actually be applied?
Sure. Think about a crosswalk, especially one in a very busy part of a city. This research suggests that in high traffic areas, it might actually be better to design slightly narrower crosswalks rather than really wide open ones.
Okay.
Because when you have a narrower crosswalk, people are more likely to be walking in the same general direction just straight across the street. This would limit the angular spread and encourage the formation of those efficient lanes.
So you're saying that a wider crosswalk, which you would think could accommodate more people, might actually cause more congestion and slow everyone down.
Exactly. It's counterintuitive, but that's what the research seems to indicate. And this angular spread metric could also be a really useful tool for figuring out when you need crowd control measures.
Uh-huh.
So imagine a major train station during rush hour or a big stadium when everyone is leaving after a game.
I can picture it.
By looking at the potential angular spread of the crowd, officials could predict when you might have bottlenecks or unsafe situations, and then they could take action to keep things moving smoothly.
So they could open up more exits,
Yeah.
direct people along certain routes, even change the timing of pedestrian signals.
Exactly. It's all about using data to manage crowds better so that people still have the freedom to move around. But everyone is also safe and things are running efficiently. This kind of scientifically backed insight is going to become more and more important as our cities become even more densely populated.
Okay, so let's recap everything for the listener. What's the key takeaway here?
The way people move in crowds might seem random and chaotic, but it's actually controlled by a fundamental mathematical principle, the angular spread threshold, which is somewhere between 13 and 16 degrees. When the angular spread is less than that, you get natural order in the form of lanes. But when it's more than that, you get chaos and inefficiency.
And this isn't just some interesting mathematical theory. This actually has real implications for how we design and manage public spaces. And it could make a big difference in how safe and efficient it is for everyone to move around. So here's something to think about as you go about your day. Consider the public spaces that you move through every day. Your commute to work, a stroll in the park, a trip to the grocery store. How might knowing about this idea of angular spread change how you see these spaces and the way people move through them? Kind of makes you wonder what other things that seem chaotic in our world might actually be governed by some hidden mathematical order. We encourage you to keep looking around, keep being curious, and keep thinking critically about the world around you.
I agree.
That's all the time we have for today's deep dive. We'll see you next time.
See you then.